So starting section 11.1, we are talking about probability. Our focus today will be looking at the terms permutation and combination. Do those sound familiar to anybody? Have you heard the term permutation before? Okay, so we're going to look at what is the difference between the two, how do we calculate them. You are going to want calculators today. If you don't have one, grab one off my desk, otherwise go ahead and dig yours out. All right, so we are going to start out just using multiplication to quickly figure out how many ways we can do things. All right, we are going to use multiplication to count the number of ways things can happen. It is called the fundamental counting principle. Okay, fundamental counting principle. It basically says if we have two different events, and let's say the first event can happen in m different ways, and the second event can happen in n different ways, then the two events can both happen in m times n ways. All right, the example that we have here, let's say I'm trying to put an outfit together and I have 3 pants to choose from and 2 shirts. If I don't worry about fashion and what matches and what goes together, I have 3 pants and 2 shirts, I have 3 times 2 or 6 different outfits that I could make. Does that make sense? All right, we're going to look at an example that deals with license plates. The one on the left is from Maryland in the year 2004. The one on the right is from Maryland in the year 1912. Okay. To create a license plate in 2004, we could use 3 letters and then 3 digits. Okay. Can those letters be repeated? Could I make a license plate that has AAA for the letter portion? Yes. So how many letters do I have available? How many letters are there in the alphabet? 26. And we can repeat them. So for the first letter, I have 26 choices. For the second letter, I have 26 choices. And for the third letter, I still have 26 choices. If I couldn't repeat them, if there was something in the description that says that you can't repeat things, then that would be 26, 25, 24. Does that make sense? Multiplication, because the fundamental counting principle says I'm just going to multiply those together. It is followed by 3 digits. How many digits do we have? Counting from 0 to 9. 10 numbers. So we have 10 options for the first number, 10 for the second, 10 for the third. Go ahead and grab your calculators and multiply that all out. All right, what did we get for a total? Yes? So 17,576,000 different license plates that could be made. Okay? In the year 2004 for Maryland. Now, if we look at the one from 1912, there are no letters being used. They're all digits. How many positions do we have? Okay? In each case, we have how many options? What's 10 times 10 times 10 times 10? Okay, now the question said, how many more of the 2004 plates did we have compared to the 1912 plates? So if we subtract those, we get what? 17,566,000? We subtract 10,000? Okay. Our next question says, in 1966, one type of Maryland license plate had 2 letters followed by 4 digits. Go ahead and set this up and check with the people at your table. All right, check your answer. 6,760,000. All right, questions on that idea of the fundamental counting principle. You're looking at different ways things can happen. Make sure you pay attention to, can you repeat the object or not? Okay. All right, our first term that we had in our objective was permutation. Permutation is arrangement of items in a particular order. So this is a case where the order matters. That's going to be really important. We're going to be talking about permutations and combinations. You have to know that a permutation, the order matters. Okay? Suppose we want to find the number of ways to order 3 items. We could use the fundamental counting principle to get 3 times 2 times 1, or 6 permutations. So again, that same fundamental counting principle that we had before. If I have 3 objects and I want to put them in a certain order, I can pick any of the 3 for the first position. But as soon as I put something in that spot, I'm down to only 2 left to choose from. Okay, so now I have 2 objects. Once I put that one in the second position, there's only 1 left for the third place. Does that make sense? So the order is important here. We can use factorial notation instead. So instead of writing 3 times 2 times 1, we could list it right as 3 factorial. That's 3 with an exclamation mark. Okay? I want you to look on your calculators, go under your math key, and then scroll over at the top to where it says probability, PRB, and look at that menu. Do you see an exclamation point? I think it's option 4. Okay. So 3 factorial was 3 times 2 times 1. 4 factorial would be 4 times 3 times 2 times 1. All I'm doing is I'm taking the number and multiplying it by all of the integers down to 1. Okay? So n factorial would be n times 1 less times 1 less than that, and I'm going to keep going till I get all the way down to 1. Okay? So 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. All right. It says, in how many ways can you file 12 folders, one after another, in a drawer? Okay, how many different ways can I put those 12 file folders? So, how many options do I have for the first folder? 12. As soon as I place one, now I'm down to 11. When I put that one in, now I only have 10 to choose from. Does that make sense? Now, we typically wouldn't write that all out because it takes a long time. We would write it as 12 factorial. Okay, so use your calculator. What is 12 factorial? What do we get? All right. Agree? Okay. So in how many ways could we arrange 8 shirts on hangers in a closet? How would we, what's the short way of writing that? 8 factorial. Yep. Grab your calculators. What's 8 factorial? All right, I saw some 40,320. Okay, questions about the use of a factorial key? So, in that example, we took 8 shirts, right? And we were hanging all of them up. So we did 8 times 7 times 6 times 5 all the way down to 1. But what if I don't want all of them? What if I said I have 8 shirts and I'm going to hang up 4 of them? That's a little different than saying I'm going to use all of them. Okay? The number of permutations of n items, so n is the total number of objects you have to work with, arranged R items at a time. So this is the total. This is how many I want to choose. Okay? The formula says NPR, so the number of permutations of n objects taken in groups of R is n factorial divided by the quantity n minus R factorial. So our example here, 10p4, means we are taking 10 objects, we want them in groups of 4. So we have 10 factorial on the top, and then we have the difference between n and R, so 10 minus 4, or 6 factorial on the bottom. Okay? So our first example says 10 track students are in a race. First, second, and third places get medals. Does the order matter? Is there a difference when I come in first versus coming in second? Yes. Usually they're different colored medals, things like that, right? It's better to come in first? All right. So order is important. If we were strictly to think of this in terms of the fundamental counting principle, how many positions are we trying to fill? 3. So we have 3 blanks. How many runners start out the race? 10. Could any of those 10 finish first if we don't think about ability and all of that? Any of those 10 could come in first, yes? But as soon as one person crosses the finish line for first place, now there's only how many running? 9 left to run. Once the second place person crosses the finish line, we're down to only 8 available. Does that make sense? All right, don't grab your calculators. What's 9 times 8? 72 times 10. All right. If we were going to set it up as a permutation, we would say there are 10 runners. We are choosing groups of 3. Okay, we have 10 runners. We're going to select the places first, second, and third, 3 places. So our formula would be 10 factorial, n factorial, divided by n minus r factorial. So 10 minus 3 would be 7. Okay? So you can grab your calculators and do 10 factorial divided by 7 factorial, or you can think about what it means. 10 factorial means 10 times 9 times 8 times 7 times 6 all the way down to 1, correct? 7 factorial means 7 times 6 all the way down to 1. So all of this, 7 divided by 7, 6 divided by 6, that's all going to cancel out, right? And we really just have 10 times 9 times 8, which is the same thing we had here. Yes? Okay. I'm going to pause the recording. I want you in your groups to try this next one. All right, so for part A, did you do 15p3? No? What did you do? Okay, so again, fundamental counting principle is the same thing, yes? You have 15 things, you're choosing 3 objects. So 15 factorial divided by 15 minus 3, 12 factorial, would be 15 times 14 times 13, yes? So again, could set it up as a permutation, could set it up using fundamental counting principle. Either way, we got what? Okay, so for part B, I wanted to explain that one a little bit. We're going back to the first example where we had 10 runners, and we calculated there was, what did we end up with? 720 ways to finish first, second, and third. This question is saying, if you don't worry about who comes in first, second, third, all the way up to 7th, if you only focus on saying, how many ways can someone come in 8th, 9th, and 10th? Would our answer be any different? Again, I have to emphasize, you don't care about who's finished first, second, third, and all that. We're not counting that. We're just saying, if there are 10 runners, how many could finish 8th place? any of the 10, right? We started a run, there's 10 kids racing, any of those 10 could come in 8th. As soon as someone is tagged as 8th place, how many are left as choices for 9th? 9. And then as we tag that person, then we only have 8. So it's still a case of 10p3. We're just worrying about positions 8, 9, and 10, the last 3 places, versus the first 3. Does that make sense? Okay. So we talked about finishing first, second, and third, and we said it matters, right? If I come in first, that's different than coming in third. What if it doesn't matter? What if I changed the question and said, the top 3 place finishers move on to the next competition? Does it matter now if I came in first or third? No, I get to advance to the next round. Does that make sense? So just by changing that one little piece, we've changed it from being a permutation, where the order matters, to being a combination, where the order doesn't matter. Okay? So I said earlier that you had to be very careful to remember that a permutation, the order matters. In a combination, it doesn't matter. Okay? And this is the trick I use to remember them. If you come up with your own trick, that's fine. But I think in terms of the alphabet. P and O are next to each other in the alphabet, yes? So permutation and order go together. Combination, C, D for doesn't. Those go next to each other. So combination doesn't matter. Permutation, order matters. Okay? Look at the formula for a combination. We're still looking at n objects taken in groups of r. Okay? The number of combinations of n items from a set chosen r items at a time. This part of it is the same thing we had for permutations, right? The extra little piece is that r factorial on the bottom in the denominator. And what that is doing is it's taking out all of the duplicates. So think about it. When we talked about a permutation, let's say I'm looking at this group of 3 students, and I'm saying, how many different ways can I arrange them at this table? Okay? There's 3 choices for who can sit in that seat. Now once somebody sits down, I have 2 options there. Once that person sits down, I have 1, right? 3 times 2 times 1. There's 6 different ways I could arrange those kids. But if I said, I don't care where you sit at the table, just sit at this table. It doesn't matter which of those 6 arrangements we use. So what this combination is doing is it's dividing out all of the repeats. It's the same 3 kids, they're just sitting in different seats. Okay? Our example, 5C3. We do n factorial, so 5 factorial on the top. We have an r factorial on the bottom, so 3 factorial. And then we have the difference between them, like we did with permutations. So 5 minus 3 factorial. Now, the parentheses there are so we can visually see what we're doing. But if we were typing this in our calculator, we would have to do 5 factorial divided by, and then a set of parentheses to group all of the denominator together, 3 factorial times the 5 minus 3 factorial. Does that make sense? And even if we change this 5 minus 3 and just wrote it as 2 factorial instead, we would still need these outer parentheses, so it divides by all of that. Okay? So we're going to try one. It says, find 13C4, the number of combinations of 13 items taken 4 at a time. So 13C4, if we plug it into the formula, would be 13 factorial divided by what? 4 factorial for r factorial times the difference, 13 minus 4 factorial. And again, you can simplify that right away and just put that down as 9 factorial. I'm fine with that. But again, if you were going to put it in your calculator, you would need parentheses around that whole denominator. Okay? So let's go ahead and figure out what that is. Anybody have it? All right, I'm seeing 715. Are we getting that? Anybody need help with the calculator? Okay, now, on your calculator, go back to your math probability menu where you've been pulling up your exclamation point. Do you see options 2 and 3? NPR and NCR? Okay, so here's the deal. That is a shortcut I'm fine with you using. However, on your test, I will be saying, and in your homework, you must show me the setup. So for example, if I were doing 8C3, what I would expect to see on your paper is that you know that is 8 factorial, you're dividing by 3 factorial, and 8 minus 3 or 5 factorial. I would expect to see that setup so that you tell me, yes, I know the difference between what a combination and a permutation looks like, how it's set up. Then you can use the shortcut on your calculator because it takes a while to pull up all those exclamation points. All right, so on your calculator, what you would put in is an 8. Then you'd go to that math probability menu and choose NCR and then type the number 3. Newer calculators might substitute that 8 and 3 into the formula for you. Some of them leave it looking just like what I've got on the board. Then hit enter, and what do we get? 56. Okay, go ahead and try that for the next one. Make sure you show the setup first, and then you can grab your calculator. All right, so checking our setup, you should have 9 factorial on the top for the numerator. Denominator would be a 2 factorial and what? 7 factorial? Okay, and what did you end up with? 36. Now, I'm assuming most of you grabbed your calculators because I said you could, right? But let's say we didn't have a calculator. 9 factorial is 9 times 8 times 7 times 6 times 5, right? Down to 1. This 7 factorial on the bottom is going to drop all of this out, correct? So it's really 9 times 8, and then we're dividing by 2 factorial. But 2 times 1 is 2. Can I reduce the 8 and 2? 9 times 4 is 36. Yes? Sometimes it's faster to do that. If you look at that and say, well, everything from 7 on down is going to drop out, I really just have 9 times 8 divided by 2. It's probably faster to punch that in than to pull up all those menus. Okay? All right, the last little piece we're going to look at is distinguishing between, is it a combination or a permutation? Which one does order matter in? Permutations, good. All right, so the first one says a chemistry teacher divides his class into 8 groups. Each group submits 1 drawing for the molecular structure of water, and he's going to choose 4 of them to put in a display. In how many different ways can he select the drawings? So my question for you is, we've got 10 tables in here, right? 10 groups of kids. If I said you're all going to submit something to me, and I'm going to just choose 4 of them to put up. Does it matter if I choose this one first, and then this one, or if I do them in a different order? It doesn't matter, right? It's still the same 2 drawings. So in this case, order does not matter. So it means it is a combination. So we have a combination of how many things? How many different groups were there? 8 groups, and we were choosing how many? 4. So 8C4. Again, you're going to write out the setup, which is 8 factorial divided by what? 4 factorial for the r factorial piece. And then n minus r is another 4 factorial. That is not the same as 16 factorial. All right, be careful. 4 factorial times 4 factorial. We can multiply the 4's together. We can multiply the 3's together. We can multiply the 2's together. That's not 16 factorial, right? Okay, go ahead and grab your calculators. Figure out 8C4. All right, I'm seeing 70. Agree, disagree? Yes? Okay. Now, what if for that same question I change it and I say I'm going to select those 4 pictures and arrange them from left to right? Now what have I done? I've made order matter. Okay? If I have a specific arrangement from left to right and I change those around, it's a different permutation. So, permutation, we had 8 groups submitting 4 drawings, but instead of 8C4, now we have 8P4. Setting it up, which you have to do before you grab your calculator, what is the denominator going to be? Just the difference, 8 minus 4 factorial. All right, so 8 factorial over 4 factorial changes it to what? All right, so if I worry about the order, I have a lot more different options, right? If I say all the orders that have the same 4 pictures in, doesn't matter what order they're in, I've cut it down from 1,680 down to 70. All right, last one. Talk at your tables. Does the order matter? And then actually calculate your answer. All right, so for the first one here, the chemistry teacher, we said order doesn't matter. This one we said order matters. Right? So we changed it to a permutation. In this last one, does the order matter? Yes. What in the word problem made you think order mattered? They win different amounts, right? So it's better off if I get first drawing, right? If I win first prize, I win more money than second or third prize. So order does matter. So you did 25P3, 25 objects, you chose 3. 25 factorial over 22 factorial. Now, remember on your calculator, you would put in 25 NPR3, right? And you would get 13,800. Okay. All right, the last little piece that I want you to look at is that chart, because we've talked about 3 different topics, 3 different ways of looking at how many ways we can make something happen. All right, the fundamental counting principle. I want you to think of the license plate example. Okay. Could we repeat objects? Yes. Could we use the fundamental counting principle if we didn't allow repeats? Yes, we did that, the 3 times 2 times 1, right? Factorials. Did the order matter? It didn't have to. We could do that when it did matter, but it's not required. Does that make sense? All right. The second part, permutations. Could we repeat objects in a permutation? Could we repeat objects with a permutation? No. Think about the runners finishing the race, right? As soon as one person crosses, they can't go back and cross again later. Okay? Well, I suppose they could, but it wouldn't make sense. So, can we use it for repeated situations? No. Same with combinations. We can't use it for repeated situations. We can use either of those when we don't repeat. Okay? So you can use any of them with a non-repeated situation. Does the order matter for a permutation? Yes. Does it matter for a combination? No. All right. So hopefully that kind of organizes how you can do these. Again, we have consolidated section 11.1 into one day's assignment, so this is your new assignment, and we will move on to section 2 tomorrow.